Good afternoon, everyone. I'm Alexandra Condili, Assistant Professor at the University of Kansas, Department of Civil and Environmental Engineering. Since the fall of 2014, I also serve as the chair of the Freeways and Multi-Lane Highways Subcommittee of the Highway Capacity and Quality of Service Committee of the TRB, and Beczaat also serves as our subcommittee secretary. Our subcommittee is responsible for reviewing, testing, and maintaining most of the Volume 2 uninterrupted flow methodologies and the respective chapters that concern the freeway facilities, the travel time reliability, and also the freeway segment topics. That means that our subcommittee is responsible for a total of 9 chapters, 5 that are in Volume 2 and 4 supplemental chapters that are in Volume 4. Actually, during the development of the Hcm 6th edition, our members and friends spent considerable effort and time in reviewing the draft chapters, testing the new material, the new methodologies, and also the computational engines like the FreeVal. Our subcommittee volunteers, and perhaps some of you are participating in this webinar, worked very closely with the contractor team who produced the manual by providing input and recommendations and finally approving the new chapters. As the needs of the transportation professionals and practitioners have changed over the years, the Hcm has significantly evolved to address these needs and provide tools that can be used to evaluate and also to compare the operational effects of various scenarios in a quick and a cost-effective manner. Now, this new edition, Hcm 6, as you will also hear in this webinar, provides several changes and new tools that are very relevant to transportation practitioners, engineers, and planners. For example, we now have the analysis methodologies for evaluating travel time reliability over a long period of time instead of doing a single period analysis. Also, we have tools to analyze the operational effects of various active traffic and demand management strategies, including managed lanes. But it's best to let our speakers talk about these new tools and capabilities of the Hcm 6. So, on behalf of the Freeway Subcommittee and the Highway Capacity Committee, I would like to welcome all of you and thank you for participating in today's webinar. And I would also like to thank Bastian Schroeder and Beczaat, who will be presenting this webinar, for their tremendous efforts and their contributions to updating the manual and disseminating and educating practitioners on its content. So with that, I'll leave it to Bastian to start with the presentation.
Thank you, Alexandra. As Courtney mentioned in her introduction, this is the 3rd webinar in a series of several webinars that are being offered through ITE, and I encourage all of you to attend and look into the other offerings as well. Today our focus is on the freeway methodologies, which are contained in Volume 2, Uninterrupted Flow of the Hcm 6th edition, with the learning objectives being what Courtney already went through in her introduction. For the presentation today, we'll start with an introduction of our speakers and the approach, and then give a brief overview of the Hcm freeway facilities methods for those of you that may not be familiar with it. The method has been around since actually the 2000 Highway Capacity Manual, but for many years hasn't been used as frequently as it could have across the country, mostly because of lacking software implementation and lacking outreach, where a lot of practitioners were unaware of the capabilities of the method. The method has been significantly improved with the Hcm 2010 and has since then seen an increasing use across the country. And now with the Hcm 6th edition, there are significant new capabilities and features that we will go over in the 3rd part of this presentation. We will then conclude today's webinar with a series of applications and case studies, moving beyond the theory and showing real-world applications of where this method is being used and has been used by agencies in different parts of the country to solve real-world transportation problems and get at solutions more cost and time effectively than more complex analysis methods like microsimulation. As a preview of the new capabilities that we will highlight in this webinar, this slide lists just some of the key changes that have been introduced into the uninterrupted flow chapter since the release of the 2010 Hcm. The travel time reliability analysis was the key driving force that led TRB to publish a new HCM relatively soon after the release of HCM 2010. But many other methodologies, such as the new work zone method, new ways to evaluate trucks on freeways and other facilities, and new planning methods, managed lane capabilities, active traffic management, including the evaluation of ramp metering and hard running shoulder and other strategies, have occurred since the HCM 2010 that really drove the need to have a very significant overhaul and major update of this manual. Other changes were done as part of the effort to integrate all these changes, such as a unified speed flow equation that بعزرت will talk about in more detail later in the presentation, an increased emphasis on calibration and guidance. Many of the new methodologies, the effect of evaluating work zones or managed lanes or weather impacts and incidents for reliability analysis, really all speak to the need to calibrate the freeway operation to what we would call non-ideal conditions. The HCM for many years has focused on ideal conditions with ideal capacity of 2,400 passenger cars per hour per lane. But as is shown in the example in the bottom right of the screen, a work zone in Southern California, clearly this particular facility is not ideal conditions due to the lack of shoulders, narrow lanes, pavement conditions that aren't ideal during work zone. And so the expected capacity, frankly, is much less than 2,400. And for a long time, the HCM hasn't given that kind of guidance, which we have now overcome with this new edition. So let me start with a high-level introduction and overview of what is contained in these chapters. The majority of the webinar today will focus on Chapter 10, Freeway Facilities, which really integrates the individual segment methodologies for basic segments, freeway weaving segments, and freeway merge and diverge segments that are contained in Chapters 12, 13, and 14. In addition, there's a new chapter on freeway reliability analysis, which will be the core focus of the next webinar in the series that is going to be offered on January 24th. And we will therefore not cover that material in a lot of detail today. Also for uninterrupted flow, there are several electronic chapters that are contained in the online volume 4. That volume is available at hcmvolume4.org and is available for anyone to access after you create a free account. You no longer have to have purchased the HCM. This slide illustrates the need for why we're analyzing freeways as facilities. What's shown here is a segment of freeway in Raleigh, North Carolina, moving eastbound towards the state capitol here. And what's in the forefront of the picture is what we would describe as a basic freeway segment. And evaluating a segment like this in isolation would show us a level of service probably of C or D or maybe even E, but certainly not breakdown conditions because, frankly, that segment in and of itself is not overcapacity. However, if I had a video to play fast forward of what this particular segment looks like about 30 minutes after this photo was taken, the queue that's seen leaving segment that creates a lot of turbulence. In about 30 minutes, this particular segment would be continuously queued, showing significant congestion. The key here is that the segment does not fail because it itself is overcapacity, but the segment fails because of downstream congestion, an active bottleneck that then spills back over time into that particular segment. The freeway facilities method is geared at evaluating exactly that type of queue interaction over space across multiple segments as well as over multiple time periods, and is thereby fairly unique across the highway capacity manual that a macroscopic analytical method can actually evaluate queuing patterns over both time and space. The Chapter 10 methodology combines the individual segment analyses for a basic merge, diverge, and weaving segment for facilities up to a length of about 10 to 15 miles or 16 to 25 kilometers. During undersaturated conditions, the methodology replicates exactly what the individual segment methodologies would estimate and just aggregates the performance across, in this case, 11 segments that are shown at the bottom of the screen here. But whenever any one segment is over capacity, the method then explicitly looks at oversaturated queue spillback conditions using a modified cell transmission model approach to track queue formulation and dissipation over multiple 50-minute analysis periods, and in some software implementations even allowing for a full 24-hour analysis of 96 such time periods. And so certainly this type of whole day analysis is fairly unique and is not easily replicated in other tools. To get everybody on the same page on what these segments are that we're talking about, here's the four basic building blocks of a freeway facility. At the top is a basic freeway segment that is described in Chapter 12 of the Hcm 6 edition. The next two examples are a merge segment and a diverge segment, which are both described in Chapter 14 and are typically defined as the area 1,500 feet downstream of a merge point or upstream of a diverge point, looking at the turbulence and friction that happens in the ramp influence area due to traffic either entering the freeway or leaving the freeway. And then finally at the bottom, a freeway weaving segment, which is typically an on-ramp followed by an off-ramp connected by an auxiliary lane or multiple auxiliary lanes that then creates additional turbulence and friction and typically has speeds that are significantly reduced over just a standard merge or diverge area. And weaving segments are described in Chapter 13. To illustrate just one example of what this methodology can do, here is a look at actually what's example problem 1 that's part of Chapter 10, the freeway facilities method, although the example problems are now contained in the electronic volume 4, so any of you can access this example problem today, even if you don't have the HCM, by going to hcmvolume4.org and creating an account. But here's a look at a facility that contains 11 segments of various types, some on-ramps and off-ramps, weaving segments, to on-ramp and off-ramps that are closely spaced, where we have some overlapping segments here in segment 9, with general attributes that you would have for a typical freeway analysis. So there's some information here of the number of trucks and buses, about 1.25%, as well as tractor trailers. A big change in the Hcm 6 edition is that we're now distinguishing between the effect of single unit trucks versus tractor trailers. So these are two separate inputs now in the new Hcm. Driver population, the free flow speed, information about our merge and diverge areas, and about the weaving segment, and then doing an analysis over 75 minutes, which is 5 15-minute time periods. And looking at the demand input data, this is the type of information that you would need to perform an analysis. So for each of your 15-minute time slices, you would require an entering flow rate, entering the facility at the beginning, and then the demand flow rates on all on-ramps and off-ramps along the facility, which then translate to an exiting flow rate at the end of your analysis. The numbers in parentheses here are the ramp-to-ramp demands for the weaving segment that I identified in a previous slide. The method then goes on to do a lot of calculations, including, for example, the segment capacities that are fixed for most of these segments, except for segment 6, which is a weaving segment. The weaving capacity changes as a function of the traffic demands, and therefore every 15-minute period has different capacity value. And then jumping ahead to the type of output that you could get out of this methodology is, one, you get a look at the demand to capacity ratios on this segment. And you're seeing here in the top chart that most parts of the facility have a demand to capacity ratio less than 1, but segments 8, 9, and 10 in time period 3 have a demand to capacity or D/C ratio of 1.1, so the degree of saturation of about 110%, which is oversaturated and therefore is expected to result in some queuing. As a result of that capacity constraint, the methodology would then translate whatever demand cannot be processed through segment 8 and actually estimate a volume served, where you see some discrepancy between the demand values that were entered on a previous slide and the actual volume that can get processed through the facility, because the method explicitly keeps track of queue propagation and unserved vehicles that are stored in that queue that are then released in subsequent time periods after the demand drops to lower levels. And then finally getting speed contour performance, as shown in the bottom of the slide, where the bottleneck in segment 8 results in Q spillback and therefore a drop in speed in the upstream segments, and that being sustained for actually longer than just the 50-minute period where the demand exceeds capacity. And this is really a key capability of the method, where the chart at the bottom, the speed contours, are not unlike what many transportation professionals these days are looking at from probe-based travel time data that are available through various software vendors or made available through Federal Highway and the NPM-RDS data set, where there's a direct comparison between the modern probe data set, segment-based travel time performance and speed performance, and what this method can output routinely. But the one thing that this method can offer that the observational data and and even simulation in some cases cannot offer is that not only are we seeing the actual performance, so the top chart is a level of service matrix that correlates with the speed contours I showed in the previous slide, where the 4 segments that are level of service F are the ones that are operating at a lower speed and also a higher density, which triggers level of service F. But the method not only gives you the existing performance that you would see from your sensors or from your simulation, but it also flags bottlenecks that are downstream of the one that's active. So in other words, hidden bottlenecks. And therefore, the method results in a key diagnostic tool that you can use to not only improve current congestion, the observed bottleneck in segment 8, but also recognize that really to solve this particular facility and to improve it, widening or ATDM improvements are needed in segments 8, 9, 10, and 11, based on the fact that the demand to capacity ratio in all of these segments exceeds 1. And so it's not only a way to evaluate the existing operations, but also to flag problems and then really diagnose them and remedy them. So with that introduction, I will turn it over to بعزت to talk about the new capabilities of the method in HCM6, and then I will return at the end to talk about some sample applications of this method.
Thank you, Bastian. As Bastian went over the new capabilities of the new HCM edition, here in this section of the presentation, I want to go in details and depth of what are these new capabilities. I would like to start with freeway and multi-lane highway segments. Going back to the HCM 2010, we had 2 separate chapters, one focusing on basic freeway segment and the other one focusing on multi-lane highways. Looking at these 2 chapters in HCM 2010, we could see that like 80 to 85% of the material of the similar and same. So one of the big changes in the new HCM is that these 2 chapters have been combined, and they are right now in the chapter that in the HCM at chapter 12, freeway, basic freeway and multi-lane segments. One of the key differences between the analysis of the basic freeway and multi-lane highway is the relationship between the speed and flow. As you can see in the 2 graphs that I have in this slide, the speed flow relationship, they look similar to each other, but in fact they are different. And the way that these differences have been characterized into one chapter, one analysis type is through a unified speed flow equation, which I will go over that in detail in the later slides. So looking into the changes in this chapter, we do have revised truck PCEs, passenger car equivalent tables, which is one of the big changes in the HCM6 compared to 2010. We have an increased emphasis on the calibration through the analysis. This is one of the points that Bastian mentioned, that not all the times we're dealing with ideal condition in freeways, and in order to bring the analysis into non-ideal conditions, we have to have these calibration procedures being transparent and documented in order to be applied. We do have driver population effects right now being handled through capacity and speed adjustment factors. This is one of the again, another changes comparing HCM 2010 to this new one. For multi-lane highways, right now we do have density and capacity equal to 45 passenger car per mile per lane for all free flow speeds. The range between level of service E and F has been changed a little bit to consider this change in the density and capacity. And looking at the graph that I have here, you can see that we do have the new speed flow curves for free flow speed of 65 and 70 miles per hour for multi-lane highway, drawn in the dashed line. These are new speed flow curves that have been introduced by new Hcm. And the reason that these are drawn by dashed line is that because they are not supported with the real-world data. The real-world data has only provided us with the other free flow speed, and basically based on the interpolation, a new Hcm provides those the speed flow models for those free flow speeds. So as I mentioned, one of the differences between basic freeway segment and multi-lane highway was the speed flow relationship, and the way that in the new Hcm these have been combined through the unique generic speed flow model. As you can see on the top of the slide, we do have this equation that has several parameters that can be adjusted for different segment types, such as basic freeway segment or multi-line highways, that can predict the speed for us based on different ranges for the flow rate. One of the advantages of this unified speed flow model is that right now we do not we are not limited for 5 miles per hour increments of free flow speeds. Previously in Hcm 2010, the speed flow models for both freeway, basic freeway and multi-lane highways has been given in a set of tables and set of equations for each free flow speed rounded to 5 miles per hour. Right now, especially with this new upcoming reliability analysis in the Hcm6, there was a need to account for other free flow speeds and not being rounded to 5 miles per hour. For example, if we want to include the effect of a severe weather condition, like let's say a rain event that reduces free flow speed by 2 or 3%, if we use one of these free flow speed curves and reduce it by 2%, again, using Hcm 2010, it had been rounded to the same free flow speed, and basically meaning that we are not able to account for those conditions. So this generic speed flow model can characterize any free flow speed and basically enable us to model all sources of those non-ideal cases that could happen. Here on this slide, I have the unified speed flow equation along with the graph that shows how it represents or estimates the speed based on the flow rate. Now, I do also have several pictures of the conditions that we typically see on freeways and that they are not ideal, like having work zone, having managed lane, having a snow event, having congestion. So these are cases that they are not ideal, and we have to account for these sources of changes in the capacity and speed. One of the things that this speed flow model equation gives us is adjustment for capacity and speed, free flow speed independently. Basically, the impact of all these conditions can be translated into the capacity and free flow speed adjustment factors, and these are already included in the equation where, including these impacts, this speed flow model can predict the speed of the freeway based on the flow rate. And as you can see, and Bastian mentioned, these are all aligned with the emphasis on the calibration through the new manual. So here I want to give an example of how this adjustment to the speed and capacity works through this unified speed flow model. Let's assume that we do have a work zone that impacts our capacity as well as our free flow speed. So first, this equation accounts for the free flow speed adjustment, where, as you can see on the graph, that reduces the free flow speed to a certain magnitude. And then our capacity also has been decreased. And as you can see on the graph, the new capacity is slightly lower than the previous capacity. And our new speed flow model will predict this speed flow model shown in the red dashed line, that being representative of the relationship between speed and flow at the time that we have this work zone. So another big change in the new HCM is the incorporation of managed lane analysis. Primarily the material that has been produced for this analysis has been produced under NCHRP 3-96 project, and the material has been spread over the different chapters. Basically, Chapter 12 has the material for basic managed lane segments. Chapter 13 has it for managed lane weave segment, as well as characterizing the cross-weave effect in the general purpose lane when you do have a traffic coming from an on-ramp going into managed lane or vice versa. Also, Chapter 14 has the merge and diverge segments for managed lane, the analysis for that. So, speaking of the new managed lane analysis, HCM 6 characterizes 5 different basic managed lane segments. As you can see on this slide, we do have continuous access, buffer 1, buffer 2, barrier 1, and barrier 2. One of the differences in characterization of basic managed lane segment compared to general purpose segment is that here number of lanes are also included in the segment type. Basically, it has been driven that the number of lanes will affect the operation of the managed lane. Of course, the separation type, which could be continuous access or marking, or could be buffer or barrier, is inside the definition of the basic managed lane segment. And considering these two, we do have these 5 basic managed lane segments in the new HCM. Here in this slide, I'm showing the capacities for these different basic managed lane segments and for different free flow speeds. But I have to note that these we are using this capacity term a little bit loosely, because managed lanes like HOV lanes or hot lanes are not meant to operate in an oversaturated mode mostly. And as such, NCHRP 396 at the time that it was collecting data to characterize the speed flow model as well as capacity, at some point didn't observe the congestion. So these numbers that you can see here in this table are, we call it capacities, or it would be more accurate to say these are maximum observed flow rates that have been seen in this managed lane segment. And obviously, if you compare it with the capacities that we have for general purpose basic segment, these are fairly lower numbers. So another difference that managed lane segment speed flow model has compared to the general purpose lane speed flow model is that first, in the linear range, which at some certain segment types, we do see a slope where whenever the flow rate increases, although we have not gone into the breakpoint and we have not gone into the not curvilinear range, still speed decreases slightly. Talking about the higher range of flow rate and where in the graph I'm mentioning that as a curvilinear range, we do see 2 different curves, one of them being a solid line and one of them being a dashed line. And this is because in the managed lane speed flow model, the speed is not only a function of the flow rate on the managed lane. It's actually, it's also a function of the density on the adjacent general purpose lane. Whenever we do have a congestion or high density on the adjacent general purpose lane, then we see a frictional effect, and where you can see the speed flow model has been shown by a dashed line. If we don't have high density on the adjacent general purpose lane, then speed flow model will be shown as a solid line. And of course, the extension of the speed flow model, the unified equation, has gone into the managed lanes, and all the curves that you guys can see here are again reproducible by that equation. So another big change in the new manual is the work zone. Primarily, the material for the new work zone analysis in the new HCM has come from NCHRP 3-107 project, where basically it provides us with a model to estimate capacity and free flow speed for the work zones, where we can get those and put it into our single equation speed flow model to predict the speed. And here I want to show you the parameters and also the equation for the work zone model in the new Hcm. I don't want to go into the details, but the reason that I'm showing these parameters is that I want for you guys to know what items have been included in the new work zone model. So one of the parameters that we have is lane closure severity index, LCSI, which I will talk more about that in another slide. We do have the indicator variable for barrier type. So concrete, cone, drum would have different impacts on the operation of the freeway when we have the work zone. Area type matters, it's urban versus rural. Also the lateral distance from the edge of travel lane to the barriers, work zone barriers, are included in this model. And we do have an indicator variable to see if our work zone is at daytime or nighttime. Speaking of lane closure severity index, it basically accounts the number of lanes plus the open rate, the number of lanes that are open compared to the previous number of lanes. As you may have noticed, a 2-lane closure work zone for a 3-lane freeway versus a 5-lane freeway will have a different impact. And this impact basically has been taken into account by LCSI. So those parameters goes into these two equations that we have for capacity and free flow speed. Basically, the capacity is modeled as first Q discharge rate model. And basically, this will predict the Q discharge rate when we have the work zone. And then by comparing this Q discharge rate to the nominal capacity, we can compute the capacity adjustment factor where it can go to the speed flow model. As well as capacity, we do have an equation for free flow speed model where also includes the work zone speed limit and non-work zone speed limit into that, and will predict the free flow speed for the time that we have work zone by comparing that to the nominal or ideal free flow speed of the facility. We can come up with the free flow speed adjustment factor and incorporated that in the speed flow model for calibration. All right, so another new material that we have in the new Hcm is the new heavy vehicle estimation method. The PCEs that are in the Hcm 2010 have been revised and have been changed in the new manual. Also, along with its adjusted PCEs, new manual also provides a mixed flow model in volume 4 for some certain conditions that we have with trucks. Basically, the way that manual suggests is that whenever we do see light grades and low number of percent of the trucks, we should go and use these PCEs provided in the exhibit 12-25 as a general number for the analysis. And one of the key things that I forget to mention at the beginning is that another big change between truck analysis in Hcm 2010 and the Hcm 6 is that Hcm 6 does not recognize heavy vehicle and recreational vehicles, RVs. Basically, the way that categorizes the trucks is through single unit trucks, SUTs, and tractor trailers, TTs. Along with the PCEs provided in the new Hcm for general terrain, there are 3 lookup tables also provided in Chapter 12, where it provides a more accurate way to estimate PCEs whenever our grades are higher than the thresholds that we have for the general PCs or whenever our truck percentages are high. So these lookup tables that they are provide the PCEs for 3 different combinations of SUTs and TTs, 30%, 70%, 50-50, and 70%, 30%. For other combination of the single unit trucks and tractor trailers, we can use interpolation and get these numbers from these tables and interpolate them and use them. Of course, equations are also available for the number of these PCs that we have in these detailed tables. So, along with the PCEs that have been given for general terrain, also those detailed tables, whenever our percent trucks are high or our grades are high, considerably high, HCM recommends to use a mixed flow model, which is documented in chapter 25 and 26 in volume 4, where it provides a separate standalone procedure to compute the speed of the trucks. And the way that it works is that first it treats the traffic stream as a combined, then estimates the speeds for auto and truck and densities. Of course, under certain conditions, truck speeds would affect auto speeds. And more detailed stuff that also are included in the mixed flow model is the truck characteristics, such as the weight to horsepower ratio. These are more inputs that we can provide to mixed flow models to give us a more accurate estimation on the speed of the trucks. Of course, the mixed flow model is a little bit complex method. As such, the computational engine also are available to do this process. Well, another big change in the HCM, as Bastian mentioned, and would be the driving force for the production of the HCM6 is the reliability and ATBM. The way that HCM 2010 was dealing with the facilities and analysis and evaluating performance measures was that it was focusing on a single day or single period analysis. And as such, it gives us an average performance measures, like average travel time across those hours of analysis. One of the things that new HCM brings is that, well, those average travel times are great, but in the real world, we do have some things that happen, like non-recurring source of congestion, such as severe weather, such as incidents, such as special events, work zones that will change travel time day by day. And as you can see on the left graph, those fluctuations in the travel time actually are caused by these sources of congestion. So basically, the travel time reliability analysis will provide capabilities to include those sources of congestion and a set of new performance measures to characterize these variations. Speaking of active traffic management, basically in HCM 2010, when we wanted to see what would be the effect of like opening a shoulder, what would be the effect of RAM metering, all of those analysis was based on a single day analysis. So we could have been gone and see what is the impact of those, but at the end of the day, we will get the results based on the comparison of the average performance measures. As you can see in the left graph, it shows before and after case for a freeway facility where some treatments, some ATBM analysis strategies that have been implemented. It shows that, well, travel times have been improved, but the improvements are not large. Looking at the right graph, we will see those two horizontal lines, which is associated with the worst day of operation of the facility in each month. So before implementing ATBM strategy, as you can see, the high travel time was much used, but after implementing those treatments, it has reduced a lot. So this picture, this image, is possible to see through the reliability analysis and incorporation of the recurring and non-recurring sources of congestion. And so ATBM analysis in the new HCM includes a set of a number of strategies that we can go and model, ranging from hard shoulder running, RAM metering, traffic diversion, variable message signs, and etc. Of course, I should mention also the way that uninterrupted flow chapters analysis works is that in order to do an ATBM analysis, first we need to do reliability analysis, and in order to do reliability analysis, we have to do the chapter 10 core method. These are sequential type of analysis that they have built on top of each other. All right. Another big change in the new HCM is the new guidance and more emphasis on the calibration. We talked about calibration of the speed flow model through calibration of the capacity and free flow speed through the speed flow model. But apart from that, looking at the facility analysis or reliability analysis, we do have a new guidance on how to go after calibrating this analysis. As I mentioned, reliability and ATDM is built on top of the core freeway analysis. So as such, first, this core method, core analysis needs to be calibrated, and then reliability, and then ATDM analysis. So here, as an example, I'm showing a little bit more details on the core freeway facilities analysis calibration. As you can see here at the beginning, well, the user needs to gather data, what is the facility geometry, free flow speed, demand, etc. And then by putting everything together, the very first thing that we need to calibrate is the free flow speed based on the guidance in the Hcm6. After free flow speed, then we need to calibrate bottleneck capacity. After that, we need to calibrate all demand. And then we need to validate compared to the observations that we get from real world. And if it doesn't match to the extent that we want, again, this procedure needs to go for another round to make it calibrated. Well, here in this slide, I want to talk about a change, which seems to be a change, but it's not a big change. I mean, this is the procedural flow chart of the facility analysis in the chapter 10 in Hcm 20. As you can see, it has 7 steps from beginning to end. What is needed, what are the steps that need to be continued in order to analyze the freeway facility. In the new Hcm, we do have a more complex flow chart, but the thing is that this basically replicates what we had in Hcm 2010, but in more details to make it more transparent. One of the changes also in this graph, it characterizes steps that needs to be done by user, or they can be done by software tools. So as you can see here, this shows a process flow for the chapter 10 freeway analysis. It looks quite complex, and in fact it's more complex than what we see in this graph. This is a high level type of process flow that shows that. So in order to do freeway facilities, or on top of that reliability, or again on top of that ATDM analysis, we do need to have access to some sort of software tools. And the good news is that Hcm comes with a set of computational engines. And these computational engines are meant to replicate the procedures that we have in the Hcm, first to aid users to perform analysis, and also on the other hand to document the detailed procedure in the codes. And one of the reasons that we don't use a software package or tool for these computation engines and we go with the 10 computation engine is that because these are mostly research-grade tools that have been developed, and it comes with Hcm, and sometimes they don't have support as well as other commercial grade software tools are. So speaking of computational engines, FreeVal is the computational engine that can perform all analysis that we have in Volume 2, ranging from segment level analysis to the facility to the reliability and ATDM. This new FreeVal version that comes with the Hcm6 has been drastically changed. Previous versions of this computational engine have been coded in Excel via VBA interface, but this one has been developed in Java, it's platform independent. It has a nicer user interfaces where it assists the user to go over different analysis. And as I said, it's capable of doing all the analysis that we have in the Volume 2. Well, the FreeVal computation engine plus its user's guide, as you can see here, they're both available in Volume 4. FreeVal 2015E, which is the associated version with the new Hcm, has a comprehensive user's guide where it talks in detail of what are the steps from installation of the software to running different procedures. Along with this user guide, we do have a YouTube page if you visit this link that's shown on top of the page, it will take you to the YouTube page, YouTube channel, where there are short videos on computational engines, including FreeWheel, on how to install, how to do the core FreeWheel maps, how to do reliability. And each of these videos are like 4 or 5 minutes. And sometimes for users it's easier to just watch this few-minute video to see whether they want to pursue on using HCM methods or not. Again, as I said, all of these computational engines plus the user guides are available in volume 4 under technical reference library. Okay, with that said, I'm pretty much done with the capabilities of the new HCM, and I would like to turn it over to Bastian for the application.
Okay, thank you, Bazad. So in the last part of the presentation, I want to go through 4 examples of how this methodology could be used or has been used in some real-world applications. The first is looking at a major freeway work zone, looking at queuing impacts, implementing the new NCHRP 3-107 methods, looking at policy decisions, lane closure requirements, as well as identifying diversion targets that could then inform a public outreach campaign. The second is another work zone example looking at lane closure sensitivity, where an agency might be interested in setting allowable work hours, estimating the queuing impacts for decisions of allowing the contractor to close lanes at 7 versus at 8 versus at 9 o'clock at night, and very quickly seeing the impacts of that. The third is an example of an interchange evaluation, looking at different scenarios and looking at even some short-term improvements that could potentially help the interchange operation, even as an interim construction solution. And then finally, a ramp metering example that shows the performance of a facility with ramp meters, as well as giving a sneak peek at what the reliability outputs will look like or do look like. That will be the focus of the next webinar. So for the first case study, we're actually looking at a facility in Raleigh, North Carolina, about an 11.5-mile stretch of freeway. This freeway is currently under construction, but the North Carolina DOT has been working on this work zone for several years now, as well as including a lot of work leading up to the construction of actual using the FreeWheel methodology, the freeway facilities methodology, to make decisions on lane closure requirements. Looking at this facility translated into HCM segments, there were actually, as part of this project, there were many different facilities that were evaluated, including portions of the actual loop road, I-440 around Raleigh, as well as commuter routes leading into the city from various directions. So here's just one example of what this facility could look like, taking the 11.5-mile work zone plus some segments upstream of it to look at queuing impacts. In this case, translating at into about 34 segments for the HCM analysis. And you can see the HCM can handle a quite complex facility here, varying lane configurations, segment 32 having 2 lanes, other segments having up to 5 lanes, multiple merge and diverge areas, as well as weaving segments. One of the potential analyses is look at actually a slightly different facility. This is a long kind of commuter route, an almost 30-mile route through the work zone that is shown as the black box in the middle, doing a pre-construction analysis shown in the speed contours. So what's shown here are speed contours. They're color-coded with green being free flow speed and red being fairly congested. So the top chart shows the pre-construction events with some queuing actually happening downstream of the work zone, some congestion, and then 2 different scenarios, the middle chart of no diversion and the bottom chart with the 20% diversion results. These are the results of looking at the work zone that would require the contractor to leave at least 2 lanes open during constructions, or what's referred to as the 2-lane pattern here. And it was evident that even with the 20% diversion in the bottom of the screen, we still have significant queuing impacts in this 2-lane pattern configuration. And so in this methodology, once it's calibrated, it's very quickly to then run an alternate scenario. This is one that looks at 3 lanes being open, and you can already visually see that the performance is much more, the congestion is much more constrained to the work zone itself, minimizing the extensive queue spillback, about 10 miles of queuing in the 2-lane pattern, and really much more manageable queuing for the 3-lane pattern with the 20% diversion, which was kind of the target that the DOT was looking to achieve. So very quickly getting this analysis and very quickly allowing for this type of sensitivity analysis that, if this type of analysis were performed in simulation, would require repeated runs and could be quite time-consuming. Taking this diversion sensitivity and the comparison of 2-lane versus 3-lane pattern a step further, here is a look at the 2-lane pattern shown in the blue line and the 3-lane pattern shown in the green line, and looking at a simple diversion sensitivity, where every data point is a new run of the methodology that just has a global diversion percentage applied to 5%, 10%, 20%, all the way down to 50%. And so from this type of analysis, it was evident that in order to get the average travel speed on the facility around 10 miles per hour, that we would look, the target would require about a 40% diversion of traffic, and to get to an average speed of 20 miles per hour, we would be looking at over 50% traffic diversion on a major freeway that carries 110,000 ADT, which was deemed to be not a realistic goal and not a realistic target, because frankly the surrounding road network cannot really support that level of diversion, nor was it expected that drivers would respond in that fashion. So with the 3-lane pattern, it was evident that even with a 20 to 30% diversion, the average travel speed could be somewhere in the 30 to 40 mile per hour range, which was in the peak hour, which was deemed to be a realistic target. A work zone of this magnitude would not feasibly eliminate all congestion, but much more manageable. And so this is just one example where, in a very quick sensitivity analysis, this method gives very powerful result that it can inform decision-making and policy for design-build contracts, looking at what kind of requirement to put on the contractor or a particular work zone. In the second work zone example, I want to take the lane closure schedule a step further here, where in addition to answering the question of how many lanes should be closed, a really important question is when can those lanes be closed? Because the evidence that's shown here, these are some visualizations from the North Carolina DOT, looking at a work zone closing it from 3 lanes original to 2 lanes or 5 lanes to 2 lanes. You notice that the numbers shown below are the net capacity reductions are much more than just the loss of the single lane. And that's because through the NCHRP research, we know that due to the friction effect and the turbulence, the work zone really has a per lane reduction in capacity even for the open lane, so that taking 1 lane away from the 3-lane freeway can reduce capacity by over 50%. And therefore, these are decisions that need to be made very, very carefully, looking to not impact the traveling public and the customers of the transportation system too much, but at the same time giving the contractor as much time as possible to conduct the work that they have to do, which is again a cost implication and impacts the overall construction schedule. So looking at this particular nightly lane closure, or looking at the base congestion here for a facility, this is an example of doing a much longer analysis. This goes from 2 p.m. in the afternoon until 6 a.m. the next morning. And so what's evident here is the regular PM peak congestion starting at around 4 p.m. in the afternoon and lasting until after 7:30, almost 8 o'clock, until the queues have dissipated. And so then the question, at what point can lanes be closed? Now clearly everybody looking at this can probably identify that closing lanes in the middle of the PM peak at 5 p.m. is probably not a good idea. But the question is, how bad is it really? And what are the trade-offs of going from a cost-benefit perspective, allowing lane closures at 5 p.m. versus 6 p.m. versus 7 p.m. versus 8 p.m. and so forth. The nice thing about this new methodology is that this is all very quickly to achieve in this model, rather than calibrating a simulation model and taking several hours or days until new results are generated. This can be done within a matter of a few minutes. So as in this particular case, I ran this lane closure sensitivity analysis here, looking at the base case, a closure at 5 p.m., we knew that would be bad. 6 p.m., we knew that would be bad. 7 p.m., 8 p.m., 9 p.m., or 10 p.m. To look at how that work zone impacts the operations of the facility, and then really allowing an agency to make much more informed decisions about when and where to close lanes on a freeway. In the third case study, we're looking at an interchange configuration, and so this is more of the basic functionality, looking at a short, about 4-mile stretch of a facility, looking at the typical interchange case here where we have a present year no build, then a future no build, and then various alternatives. And what's interesting here is that there's one alternative listed here as 2B, that it was actually added after the initial analysis using the Hcm. And so here's how these different analyses look like. It basically is a facility where in this long segment 7 there is the question of adding an additional interchange, and really the alternatives 1 and 2 differ in the way of whether that is a half interchange or whether it's a full interchange, where the half interchange has only the on-ramp in segment 10 versus the full interchange that has an off-ramp followed by an on-ramp. In looking at the results of these, the blue lines here are the total vehicle hours of delay, going from relatively low delay in the base case to significant delay in the future no build, and then both alternative 1 and alternative 2 offering a relief in the delay, but maybe not to the levels that would be interested in. And the 2 lines comparing, the green being the free flow travel time, the red being the average travel time across the analysis period. So alternative 2 still showing some significant congestion. And so we were able, through this analysis, to actually identify a potential alternative 2B, and that was directly identified through these results that I talked about early on in the presentation, looking at the demand to capacity contours. And specifically looking at these outputs, as opposed to looking at the performance of where the queuing is and where the speed is, I'm looking at the diagnostics here on why is there queuing. And so in particular, the queuing that's observed here in this particular analysis is a result of segments 4 and 5 really being the ones that show a demand to capacity ratio greater than 1. So interestingly, the queuing had very little to do with the actual interchange that was being evaluated, and had more to do with an upstream location here, where this on-ramp in segment 4 adds significant traffic to the facility, and then once the auxiliary lane is added in segment 6, the demand to capacity ratio drops below 1, but really this being the key analysis. And so through that, we were then able to look at a potential alternate configuration, looking at, can we build the auxiliary lane earlier? Can we create a lane add in segment 4? We don't have a capacity problem before. We don't have a capacity problem after. And sure enough, with these additional changes, that's where alternative 2B comes in, really showing overall drastic improvements. So the point in this case study is that because of the diagnostic capabilities, because this is a planning level tool, macroscopic level, where the entire facility is transparent in terms of what the demand to capacity ratios are in any segment, it allows for this type of diagnostic that can be much more difficult to achieve when looking at either sensor data or even when looking at a microsimulation analysis, where both of those give you the existing conditions, but it really becomes more of a trial and error where you try something and see how well it works, versus the Hcm method is a direct diagnostic tool, which in my perspective really sets it apart as a very powerful method for looking at freeway operations. And then the last method, looking at a ramp metering feasibility, so introducing some of the active traffic management capability, asking questions like how does the ramp metering affect the congestion on the freeway, as well as how does it affect the whole year reliability, and also what is the temporal operation of ramp metering? How can that impact congestion? During what hours of the day would be looking at ramp metering? And I should note that this is just an old stock picture here. This is not the actual facility that has been evaluated. So the Hcm method would be able to do a single day operation where we're looking at a before and after evaluation of ramp metering. This is just one of the days. Clearly operations on freeways change from day to day, but the impact here is somewhat subtle. You can see some performance measures here at 7:38, 8 o'clock. Slightly better performance once the ramp meters have been activated, but then certainly some of the peak morning congestion that cannot be handled by this particular ramp metering implementation, which also wasn't the overall objective. The objective was to make travel more reliable across many days, and so that really sets us up then for performing a reliability analysis where the Hcm can now take that single day, the calibrated base performance, evaluate a strategy like ramp metering, and then not only look at the average day, but look at the whole year performance, where that scenario is replicated 250 times to signify or to represent all working days across the year, with varying demands, with randomly generated incidents and weather events, where we can then begin to quantify the overall effect of that ramp metering on the reliability distribution. And so what's shown in the bottom right of the chart here is having the red before conditions and then an overall shift of the reliability curve to the left to a lower travel time index, meaning less delay, more reliable traffic, more reliable travel with the ramp meterings being implemented. And then taking that a step further, so we have now already run 250 scenarios, all of them with ramp metering implemented. Clearly that's already a very big labor-intensive task if that were to be performed in a simulation environment. But with this Hcm method, we can now go a step further and saying, well, what is the optimal temporal application? And so it's similar to the work zone example, just a sensitivity analysis shown here of, well, if we turn the ramp meters on for an hour versus 2 hours versus 3 hours, how does the performance impact? How does the reliability change? And you see here that the method shows measurable results in the form of shifting the reliability distribution further and further to the left, as well as impacting the average a little bit, but then mostly these higher ranking, the 80th percentile travel time index, making the overall travel more reliable. So as a few closing thoughts before we turn over to questions, the Hcm 6th edition freeway method is a very robust tool set. It has been around for a long time. The method has been very thoroughly researched, tested, validated. It has been around for 15, 16 years at this point, being first introduced with the Hcm 2000. But with the Hcm 6th edition, the Hcm really has upped the game here with new reliability methods that we'll talk about more in the next webinar, the managed lane, the truck methodology, as well as these effects of non-recurring source of congestion, work zones, weather incidents, and then ways to counteract those with ATDM strategies. Also increased guidance on calibration, as Bezat mentioned, and the specific tools to implement capacity and speed adjustment factors in the methodologies. And with those methods, really there is a variety of applications, ranging from very easy back-of-the-envelope planning methods that are now available, that were the focus of the previous webinar for the Hcm planning guide, to really having performance monitoring, looking at design questions, planning questions, a range of applications that includes forecasting travel time reliability, many of them that cannot feasibly or practically be performed within simulation. And then finally, a revised focus of the Hcm to really be a resource for the modern practitioner. The Hcm recognizes that software is more and more common. It is the only way to implement many of these more complex methods, including the freeway facilities methods. So therefore, the Hcm has been now rewritten in a way that focuses on the use of software, focus on calibration and how to interpret those results, makes some computational engines even available, and then gives many, many examples in application guides in that online volume 4, similar to the examples that we have gone through in this presentation. So with that, we hope that you enjoyed the webinar today and that you will continue to attend even future meetings with the one on January 24th, really having a focus on the reliability performance. And with that, we'll turn it over to questions.
Great. Thank you so much, Bastian and Bazad and Alexandra. All great, really great presentations. I apologize for anyone who may have experienced some in and out for our audio. You should receive a recording if you had any difficulty hearing any of the presenters speak. And I apologize again for any audio issues that you experienced during this presentation. Before we go any further, so take 30 seconds to a minute to type in any questions that you may have had during today's presentation. We've received several questions that have come in already, so we will go ahead and begin. All right, so the first question that we have, whoops. Are breakpoints the same for freeway and multi-lane in the speed volume curves? Again, that's our breakpoints the same for freeway and multi-lane in the speed volume curves?
Yeah, good question. I can handle that one. The breakpoints are slightly different, so they have not been adjusted. The two methods have been streamlined, and they are now using the same equation form. But just as with the Hcm 2010, the breakpoints for multi-lane highways still all occur at the same flow rate, independent of free flow speed, whereas for the freeways, the breakpoints, they occur at lower flow rates the higher the free flow speed goes. And so this maybe one thing to emphasize is that if you're performing a freeway or multi-lane highway analysis between the Hcm 2010 and the Hcm 2000, your results should not change, at least when it's an unadjusted, uncalibrated model. So the freeway speed flow curves as well as the multi-lane highways are exactly the same as they were before. They are now expressed in a new equation, and they allow for more flexibility through calibration, but the results should not change.
Great, thank you. Another question that came in, where did the 15-minute period analysis come from? Is this just for freeways? The entire highway capacity manual is focused on the 15-minute analysis. So the Hcm methods have always been focused on the peak 15 minutes, where you would, as an analyst, take your design hourly volume, divide that by the peak hour factor to get the peak 15-minute flow rate expressed in vehicles per hour. So that framework exists throughout the highway capacity manual. What's unique for this freeway facilities method is that you can evaluate multiple of those 15-minute periods, so taking that consistent 15-minute application but replicating it multiple times. Great, thank you. On slide 26, regarding managed lane capacities, why is the capacity for continuous access higher than buffer 1 and barrier 1? I can repeat the question if you need me to. So on slide 26, okay, go ahead.
Yeah. Well, the thing that those are based on the observed flows on the real world. We have observed a higher flow rates for continuous access compared to barrier 1 and buffer 1. And maybe it's because, when you have only one lane and you have buffer or barrier next to you, it may affect the capacity versus in the continuous access or marking, you don't have any object on the side of the lane.
Okay, thank you. How does a case of Alt 2A without auxiliary lane cause more delays on main lane than with auxiliary lane of Alt 2B on slide 59 or on page 59? How does it go ahead?
Yeah. Mm-hmm. Yeah, I think the answer to that is that the volumes change. I can't speak too much about the actual location here for this project, but between all the alternatives, there were new travel demand modeling runs performed to get different traffic volumes, and so the differences between alternatives are not only in the geometry but also in the underlying volume. So the biggest difference between alternative 1 and alternative 2 is that with a different interchange configuration, the travel demand model had assigned very different flows to the facility, which then therefore changed the overall congestion pattern. So I apologize if that was confusing, but yeah, the alternatives vary by more than just the capacity. They also vary in volumes through the travel demand modeling effort.
Okay, thank you. Okay, this is in regards to FFS, free flow speed. So is FFS at grade arterials, aren't they the same thing as FFS at for freeways?
Can you please repeat it?
Sure. FFS for at grade arterials is not the same thing as FFS for freeways?
Well, arterials and freeways are different things, and those are different as well. Whatever we talked about. I think. Yeah, go ahead.
Yeah, I think so. With freeways, I think the biggest difference is that for freeways, the free flow speed is actually an obtainable and observable metrics, right? So it's typically defined as flow rates under 500 vehicles per hour per lane, which occur during nighttime conditions and therefore can be measured directly. For arterial streets, the HCM does use the concept of free flow speed, but it is more of a theoretical construct, mostly because arterials, even during low volume conditions, incur some delay through traffic signals and so forth. So both volumes in the HCM use the concept of free flow speed, but it is true that it's defined slightly different. It's a little more unambiguous for freeways because it can be directly measured and observed as opposed to arterial.
Great, thank you so much. All right, we'll move on to the next question. What are the confidence interval and level for truck calibration tables and FFS 70 and 65 fundamental diagrams? What are the confidence interval and level for truck calibration tables? And FFS 70 and 65 fundamental diagrams. I'm wondering if they meant where are they, or
Yeah, I think that second question is a little bit more straightforward to answer. The truck methods, similar to much of the new material, were the result of very detailed NCHRP reports, or in this case, NCFRP, the National Cooperative Freight Research Program, project number 41. So the final reports for that project would provide all the details. The HCM traditionally has not been reporting confidence intervals, even though for some of the newer research that is now available, but that traditionally hasn't been in the HCM, but the focus was on the average values. This is maybe a good opportunity to again emphasize the HCM volume 4, which in addition to some of the supplemental chapters and the computational engines also houses a technical reference library, and it's organized by chapter. And so for any chapter, in this case for the freeways, you can go to the technical reference library and find the original research documents that would give you that additional documentation. And so this question is a great example of something that maybe information that's not contained in the HCM, but the HCM for any of these tables would have a footnote that tells you where the research came from, what it's based on, and then the technical reference library contains those resources for additional reading and to answer questions like the confidence intervals.
Great. And although lane width factor is included in FFS estimation factor, why not in FFS estimation for factors on curvature and grade?
Can you please again repeat it?
Yes, although lane width factor is included in FFS estimation factor, why not in FFS estimation for factors on curvature and grade?
Well, I guess this free flow estimation model in the new HCM comes from directly the previous HCM as well, and it's based on a research that's how they have come up with this equation. I don't know the reason that those other parameters are not in that is because of not having enough available real-world observations, or maybe that research team, which I don't know, it's not on the top of my head, that who did that, may have come to this conclusion that it's not it's not an influential factor.
Okay. Could you please restate the website for the software?
Yes, it's volume 4 of the HCM, and the website should be hcmvolume4.org.
Okay, thank you.
I should, if I could plug into the previous question just very quickly. As Bazat mentioned, the HCM models are subject to the type of data that is available. And so for the particular data set for the free flow speed estimation for freeways, which was last redone for the HCM 2010, which was done under another NCHRP project, data were collected, but the data did not include sufficient sites with lane widths that were below 12 feet. And so therefore that factor does not show up in the equation for free flow speeds. Now there is work ongoing right now, as you know, just as there has been a lot of research between the HCM 2010 and today, research is continuing to be applied, and one of those projects, Federal Highway, is sponsoring research that looks specifically at the operational effects of narrow lanes on freeways, and so we would expect in the next couple of years to see some updates there, and maybe get to the question of free flow speed as well as capacity effects due to narrow lanes.
That's great, thank you. Okay, so we have another question that has come in. Who to contact for FreeVol support questions?
Are they asking for contact for FreeVol support?
Yes, if they have any questions as in regards to FreeVol.
Yeah, they can either contact myself or Bastian for FreeVol support.
Okay, so I will type that information into the chat pod here momentarily. Why not showing congestion in section 11 on page 17?
Bastian, I guess this is your slide. I can.
Yeah. Why not congestion in segment 11 on page 17? So I think the question is, even though the segment shows up as demand being over capacity and it's flagged as level of service F for that reason, why is no congestion observed in that segment? And the reason is, presumably that's the question, the reason is that segment 8 is what we would call the active bottleneck. And so as a result of that bottleneck having a demand to capacity ratio of 1.1, that means essentially 10% of the demand cannot make it through that segment and is instead stored in the form of a queue upstream of segment 8, in this case in segment 7 and 6. So the true demand at segments 9, 10, and 11 is not realized, and because of that the actual observed operations are non-congested. Now, in a hypothetical case where a widening project were to go in that improves segment 8 and maybe 9 and 10, but leaves 11 untouched, the analysis would suggest that then segment 11 would become an active bottleneck because that prior metering of the demand no longer takes place, and then that previously hidden bottleneck would then be activated.
Okay, thank you. Can 2 lane off-ramps with designated off-ramp lane and 1 option off-lane be analyzed? So that was, can 2 lane off-ramps with 1 designated off-ramp lane and 1 option off-lane be analyzed?
Yeah, a good question. So the Hcm is generally, for example, in that type of configuration, even if it's in a weaving segment, would be able to evaluate the turbulence that happens as a function of different lane configurations, whether that's a single on and 2 off or 2 on and 1 off. So these configurations are evaluated. 2-lane off-ramps can also be evaluated. The biggest limitation that the method currently has is that if that off-ramp is over capacity, the queue spillback effects onto the freeway are currently not modeled. So they are flagged as being level service F, but the queue propagation is not modeled. Similarly, if you have an off-ramp that spills back because of a congested arterial signal, that queue spillback is also currently not evaluated. There's currently a research project underway that looks at an Hcm system methodology. That's project 17-57, I believe, that looks specifically at that type of interaction between arterials and freeways. And there's another research project that is expected to start sometime next year that specifically looks at oversaturated freeways, which again would look more closely at the queue spillback and queue interaction effects. So that is one of the limitations currently in the methodology, to where that queuing cannot explicitly be evaluated. The method would flag it, and then would be an indication that then the Hcm, maybe is insufficient, and that an analyst might want to look at an alternative tool to like simulation to get the performance for that configuration.
Great, thank you. Okay, we have several more questions that have come in. We have actually passed our webinar time. If the presenters are available to stay on a few more minutes, I'll just go over how to earn PDH credit for those who are still on the line. Online right now. I'll go over how to earn PDH credit, and then any remaining questions will take a few more minutes to answer them. Hold on one moment.